I did put up your test scores today. I put them in this morning, so if you have not seen those yet, then can check that out today. Remember, you have the opportunity to correct and retake those. You have until we take the Chapter 9 test, which will be a couple of weeks. Just keep in mind that your test scores are the best opportunity for you to improve your grade. So like when you get to the end of the semester and you're wanting to be like, hey, like if I have a 79 and I really feel like I want to be, all of the tests throughout the semester are going to be your opportunity to get that grade up just a little bit, okay? I truly feel, and I know I've said this before, but I'll keep saying it again, if you come in and go through your test with me and correct everything and retake it, I would say 95% of the time, maybe more than that, people improve, okay? And sometimes it's 10%, sometimes it's 20 or 30%, depending on how you did on the first go-around. And that's pretty immense on your grade, because if I can raise my grade from, like, let's say I get a 60 on the first test to an 80 on the second test, you get to keep the 80, and that's it from a D to a B, okay? And so that's a really, really big part of your grade. So keep that in mind. I don't feel like I had as many people take advantage of like retaking Chapter 7 as maybe could have. And anybody, no matter what your grade, has the opportunity to retake. So if you got like, let's say a 75 and you feel like I could get up to a B, then it's worth it, right? You cannot hurt your grade when you retake. You can only improve. So if you happen to retake it and you get a lower score, then you would still get to keep the higher score. Okay, so just things I want you to keep in mind. I'm here every morning after school. You can come in, get some help, correct it, and then we'll find a time for you to retake it, okay? Chapter 9, we are going to be doing a lot of different things. The first couple of days are pretty straightforward. In fact, we've probably seen some of this stuff before. And then we're going to get into some things that we haven't done before. And the one thing that will stay consistent throughout Chapter 9 is we're going to continue to see right triangles. So we're going to talk about right triangles and doing some different things with them. Hello. So we're going to start today with the Pythagorean theorem, today and tomorrow, and then eventually we're going to get into special triangles and what we call trigonometry. Okay, and I won't talk about it too much yet, but there are some buttons on your calculators that we've never used before that we're going to be using a lot this semester, or this chapter especially, and what I tell you that for right now is because if you don't have your own calculator that you use all the time, then you probably want to make sure that you get one in the next couple of days. Because you want that to be the calculator that you use over and over again. If I go home and work, that's the calculator I want to use. I do have some that you can use, but you can only use those in class because I got to keep them here for other students. And so you don't want to be doing stuff on one calculator and then doing it at another calculator at a later time, because all calculators are a little bit different. The sequence that you type things in is going to be a little bit different. So I highly recommend, if you do not have your own calculator, to get one. If you want to know if yours is okay, most scientific or graphing calculators are fine. There's a button on your calculator that says, it looks like sin, but it's pronounced sine, S-I-N, C-O-S, and T-A-N. Those are the three buttons that we're going to be using later in the chapter. So if you see those three buttons and have wondered what they are, we're going to find out here in about a week. All right, so today we're talking about the Pythagorean theorem. Before we start talking about the Pythagorean theorem, we're going to do a couple of warm-ups because we talked about this a little bit last week. And when we write our answer, sometimes we'll go to a decimal, but a lot of times we're going to leave our answer to the nearest or in what we call exact value or simplest radical form, rather than rounding to the nearest tenth. So if we were to solve this one here, 13 squared would be 169. 25 squared is 625. And the reason we have our equation written like this is because we're going to see our equation like this a lot today and tomorrow as well. We're going to subtract 169 from both sides. So 625 minus 169 gives us what? 456. Okay. Now, here's the part that makes this a little bit hard. When we do the exact value here, we don't want the decimal. We want to leave our answer as an exact value. You're going to see that terminology a lot throughout this chapter. And so we're going to get in the habit of trying to leave our answer like that. And we did that a little bit last week as well. We're going to take 456, which is a fairly large number, and we're going to do the tree with it. And we're going to try to find something that goes into 456. And you can use anything that goes in there. If it's an even number, an easy thing to start with would be 2. 2 goes into all even numbers. So how many times does 2 go into 456? Or 456 divided by 2? 228. Okay, 2 is prime, so I circle it. We're done with that. And then I'm going to keep breaking down. Keep dividing by 2 if it's even. 114 could break to 2 and 57. Does 57 have anything that goes into it? 3. Okay, so there is what we call the prime factorization. If we were to write that out, we would go 3 2s, a 3, and a 19. All of these numbers are prime. That's why we call it the prime factorization. There's nothing else that goes into those numbers. That's how I know that I'm breaking it down as far as I can break it down, right? And what we're looking for, and this is what we talked about last week as well, we're looking for pairs. What do I have a pair of? So I have a pair of 2s. They come out. When I bring that pair out, well, I'm not going to bring out 2 2s. I bring out what I have a pair of, which is 1, 2. Left on the inside that did not pair up is a 2, a 3, and a 19. So if I multiply 2 times 3 times 19, what's that give me? 114. Yep. There we go. Okay. 114. Okay, so this is what we call our exact value. Okay, over here. When I square a square root, okay, if I were to take radical 5 times radical 5. When I square something, I'm multiplying it by myself, or by itself, right? And that's what I'm doing here. I'm squaring radical 5. What would I get if I took radical 5 times radical 5? You just get 5, okay? Because radical 5 times radical 5 is really radical 25, but the square root of 25 is really just 5. So the rule here is when I take a radical times itself, the radical disappears, and I just get the number that was underneath. But that's only if the number is the same. Like if this was radical 5 and radical 3, that's not going to happen, right? But as long as these two numbers are the same, when I take a radical times itself, it just gives me 5. So this would just become 5. And this is 144. Subtract 5 from both sides, and I get 139. Okay, what goes into 139? And sometimes that takes a little bit to try to figure out, right? 2 does not, because it's not even, right? So we don't even have to try 2. What about 3? Does 3 go into 139? Nope. Okay, 4? 5, definitely not. 6? We're going to keep trying to do it until we can't find anything, okay? And then what we might find out is 139 might be prime. There may not be anything that goes into it, okay? There are some numbers that are prime. So if there is nothing that goes into 139, then that's our answer, okay? It seems like we're missing something, like there's something else that needs to be done, but there really isn't. Because if there's nothing that we can take it down and break it down, then sometimes we can just leave our answer just like that, okay? But over here, we don't want to leave our answer as radical 456, okay? If we can break it down, we break it down. If we can't, then we leave it as is. So those are the things that you really got to pay attention to. And sometimes, especially when the numbers are bigger, it's kind of hard to find out what goes in there, right? And you have to do a little bit of work when the number's a little bit bigger. Okay, Pythagorean theorem. This is something, I would say this theorem is probably the most used theorem in geometry. And you might say, well, we're already like almost 3/4 of the way through the year and we haven't used it yet, but we are going to use it a lot the rest of the year. This theorem right here, we will use it a lot in different things that we do for the rest of the semester. So it was developed by a mathematician named Pythagoras. And so that's when you develop a theorem, then you get to name it after yourself. So Pythagorean theorem was developed by the Greek mathematician Pythagoras. And it basically, first of all, it has to be a right triangle. If the triangle is not a right triangle, we can't do the Pythagorean theorem, okay? And that's going to be the overwhelming theme throughout this chapter. All of the triangles that we're going to be looking at are all going to be right triangles, which means they're all going to have a 90-degree angle somewhere in them, okay? We're going to be doing different things with them and using different things, but today we're focused on the Pythagorean theorem. In a right triangle, we have three sides. The two sides that form the 90-degree angle are what we call the legs, okay? A and B. And those two can be interchangeable. And what I mean by interchangeable, I could label this one A and this one B. It doesn't matter which one's A and which one's B, they're both the legs. So the two legs are A and B, whichever way you want to do it. C is the one that matters. C is what we call the hypotenuse. And I know we've heard that word before. We only use that word when we have a right triangle. We will use that word a lot throughout this chapter because we're going to be dealing with right triangles a lot. The hypotenuse is always the longest side. It's also the side that is opposite the 90-degree angle. So when I don't know the lengths of these three, and we won't always know the lengths of all three of them, and you might say, well, I can look at C and notice that it's the longest, and that's probably the case, but it's also the side that does not touch the 90. Here is C. C doesn't touch the 90. C is the side we call the hypotenuse. All of these triangles are going to be drawn just a little bit differently. They're going to be turned and rotated, and all kinds of things are going to be happening. But you can always identify the hypotenuse because it's across from the 90. Okay, these numbers down here, these are what we call the Pythagorean triples. These numbers satisfy the Pythagorean theorem. So for instance, I could do 3 squared plus 4 squared equals 5 squared. This is my A, my B, and my C. I could put those three numbers in. 5 is the hypotenuse because it's the biggest of the three sides. And 3 squared is 9. 4 squared is 16. So we go 9 plus 16 equals 25. And that's a true statement, right? Now, I'm not going to go through and do that for all of these groups of 3, okay? But I could do it for any of this group of 3. So for instance, on this one here, I could do 24 squared plus 45 squared equals 51 squared. And it would be true. It would satisfy the Pythagorean theorem. And all of the numbers here are whole numbers. There's no decimals, there's no fractions. They're nice whole numbers, okay? So these would be the sides of the triangle. And some of these you're going to look at and you're going to recognize and you're going to notice, especially as we go more and more through this. These are the 4 basic ones: 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. And the reason down here at the bottom, I could do it by any scale factor. So like for instance, if I took all of these numbers here and multiplied them by 3, that would give me here. I could multiply all these by 4, and I could have a new group of numbers. Same thing here. I could take all these numbers by 2, and it gets me here. Multiply by 3, and it gets me here, okay? So we can take all the numbers and multiply it by some scale factor, and it can get me up to another group of numbers, okay? And that's the same all the way through all of these groups. So we call those Pythagorean triples. So you're going to have a couple of questions today that are going to ask you, is this a Pythagorean triple? And we have to, first of all, wonder, does it satisfy the Pythagorean theorem? Does it make this work? And are all my numbers nice whole numbers? We don't want any decimals. We don't want any fractions on our side lengths. Pythagorean triple. Because if I look over here, those are 3 sides because there's no decimals or fractions, okay? Decimals especially. Okay, so here's what we're going to do. We're going to solve for a missing side today. And the one thing you're going to ask yourself first of all is, what missing piece do I have? Is it a leg or is it the hypotenuse? That's where you got to really be careful. And so like on this one here, these are my 2 legs. And what I told you a few minutes ago was, it doesn't matter which one's A and B. I could call this one A and this one B. They're the 2 legs, they're interchangeable. So you could go either way with them, but in this case, the long side is C. It's also across from the 90. It doesn't touch the 90, okay? Those are the things today you're gonna have to pay extreme careful of. And make sure you know which sides we have and which side we're trying to find. So in this case, when I write out my equation, it's A squared plus B squared equals C squared. That's the Pythagorean theorem. We're going to use that over and over and over again today. So we're going to go 5 squared plus 12 squared equals C squared. And the reason why it doesn't matter which one of these is which is because if I do 5 squared plus 12 squared, or 12 squared plus 5 squared, I get the same answer either way. 2 plus 3 is the same as 3 plus 2. Okay? Order does not matter. So in this case, I have 25 plus 144 equals C squared, which gives me 169. Okay, and you're going to start to recognize some of these numbers because we're going to see them over and over again. But if I take the square root of 169, what do I get? 13. So the 3 sides are 5, 12, and 13. And so we would say, yes, this is it gives me 3 side lengths. Okay? So we would say, yes, it forms a triple. If I get sides that are decimals, then it would not be a triple. It's still going to satisfy the Pythagorean theorem, but it's not going to be a triple because it's not a whole number. Does everybody know where the square root button's at on their calculator? You're going to need that a lot today. If you don't know where that's at, let me know. I can help you. I think we've used that before, so I'm not going to spend too much time talking about that. Okay, A, B, and C. Once again, these 2 are interchangeable. Here's my 90, so these are the 2 legs. Okay, I could make this one A and this one B. It doesn't matter. Okay, I can't stress that enough. You don't have to decide which one's A and which one's B because it doesn't really matter. When I write this one out, I'm going to go x squared plus 3 squared equals 5 squared. Okay, that's why it's so important. We don't want to go 3 squared plus 5 squared because they're not the 2 legs. So that's why it's different than the first one that we did. You have to notice which one's the hypotenuse. The hypotenuse is always the C. And then when I solve it, it's going to be slightly different here. I'm going to subtract 9 and then take the square root, and I get x equals 4. Okay. This time, it's a leg. So my 3 sides here are 3, 4, and 5. 5 is the longest side. And yes, it forms Pythagorean triple because we don't have any decimals. They're all nice whole numbers, and they satisfy the Pythagorean theorem. Okay, down here. A, B, and C. That's how I would start off every single one of these problems. Identify A, B, and C. And these two, once again, can be interchangeable. So we're going to go 7 squared plus x squared equals 14 squared. And that's why you really want to pay attention to where that 90 is at. The two sides that touch the 90 are your A and B, and C is across from it. I don't know for sure if this is the longest, but because it's across from the 90, it really is the longest. So if we go through and solve this, square both of those numbers. We're going to subtract 49 from both sides. What's that give me? 147. Okay, what happens when I take the square root of 147? You get a decimal, okay? So, first of all, we don't want a decimal. We want an exact value. We know the exact value is not a whole number here. So the first thing I'm going to say is that this is not a triple. So when it says, is this Pythagorean triple, we would say no, because my third value is not a nice whole number, like it was on the first two that we did, okay? So that's the first question that we're going to answer. Now it says, write your answer as an exact value. On those very first two problems that we did on the notes today, before we kind of got into everything, we talked about breaking this down. So we have 147. We're going to try to find something that goes into 147. 3. Okay, how many times? 49. Okay, and then 7 times 7 is 49. I'm going to move it over here just because I have more room. So I would go 3 times 7 times 7. I have a pair of 7s. That's what's going to come out. So this would become 7 radical 3. And that would be my answer. That's what we call our exact value. We don't want the decimal answer. There are times where we will use the decimal answer, and we'll talk about that here in just a second. But if we're just doing a basic old triangle, typically we're going to leave our answer in exact value. Okay, on this one here, 4 and 6. Which two sides do we have here? A, B, or C? Let's do this. What would X be? Be what? Is X going to be A, B, or C? It's going to be the C. Okay, how do we know that X is the hypotenuse? It's across from the 90. Here's the 90, X is across from it. Okay, everybody see how we figure that out? It does not touch the 90. It's the only side that doesn't touch the 90. Never meets up. These two. Now, does it matter which one's A and B here for the 4 and the 6? No. So I could label 6 as A, or I could label 6 as B. Same thing with 4. Those two are interchangeable with one another. The one that matters is the C. Okay? No doubt about it. So then we're going to go 4 squared plus 6 squared equals C squared. Okay? And if you wanted to put X in here, you can. X is C, so whether you call it C squared or you call it X squared, we're talking about the same thing. So I've got 16 plus 36 equals C squared. So I get 52 equals C squared. Okay, know your perfect squares. And yeah, you can put it into the calculator, but if I take the square root of 52, do I get a nice whole number? No, right? I mean, when we talk about perfect squares, we're talking about numbers like 25, 36, 49, 64, things that when I take the square root of them, I get a nice whole number. Those are numbers I should be able to recognize, hopefully not even have to put it into my calculator. There's nothing wrong with putting it into the calculator, but we should be able to start recognizing those numbers. Those are numbers that are going to pop up more often than not. So when I take the square root of 52, I do not get a nice whole number. So we're going to break it down. So first of all, this is not a triple, because if I took the square root of 52, I would get a decimal. We don't want a decimal. And we're going to break 52 down. Something that goes into 52. Anything. It's even. So what goes into all even numbers? 2. Okay? 26 is not completely broken down. So we'll go 2 times 13. Those are all prime. So we would have 2 times 13. We got a pair of 2's. 13 stays inside. 2 radical 13. Okay. Any questions about simplifying radicals or identifying sides? Everybody good with that so far? Okay, now we're getting into some story problems. Okay, and we kind of talked about this last week briefly. When we do a story problem, like we had one on the test on Friday where we had the statue and we tried to find the height of the statue, right? And when we try to find the height of something, whether it's a building or a statue or whatever, we don't really use radicals. Like we wouldn't use that to say, oh, that building looks to be like it's 2 radical 20 feet tall, right? That just doesn't make sense. We wouldn't use that in our normal talking to one another, right? So when we are doing something that is an actual height or length of something, we're going to write our answer as a decimal. So essentially, if I'm doing a story problem, we're going to leave our answer as a decimal because that would make a whole lot more sense. This building or whatever is about 22.3 feet tall, okay, or whatever it might be. So in this case, if it helps you to redraw the triangle, then redraw the triangle. Okay, sometimes on these pictures it's kind of hard to see what you've got. We got a 90-degree angle. Okay, the height right here is 47.57. Those are your support beams. Okay, the skywalk going across here, it's saying 23.6 is this is the halfway point of these 2 triangles. So you've got these 2 support beams here. We're trying to find the length of this support beam. So the support beam, whichever way you want to look at it, would be C. So I think just redrawing a triangle is helpful. Most of you might be able to do that without redrawing the triangle, but that's what it would look like. Okay, and once again, it doesn't matter which one of these is which. And we're trying to find our C value. A lot of times it'll tell us what to round to. So just kind of be careful here. So let's put this into our calculator. And on most of your calculators, you should be able to put this all in at once. You can do it separately if you want to, but most of you should be able to go 47.57 squared plus 23.26 squared, whatever we've got. And we're going to take the square root of that. Okay, don't forget to take the square root at the end. So try putting this into your calculators just to make sure you know what you're doing here. Okay, and then we're going to take the square root of that number. It kind of depends on your calculator. When I get to this point right here, some of your calculators, it's going to give me like 2803.9325. Okay. Some of your calculators, I can just hit square root right now and it'll give me the square root answer. Okay. Some of your calculators, you have to type that whole number in, but rather than typing that whole number in, you can hit square root and then you can hit second answer, or you're going to look for this button on your calculator. It takes that whole decimal number and it puts it into your calculator for you, so you don't have to rewrite that entire number over again. If you're not sure where that's at on your calculator, let me know and I'll be glad to show you. Okay, it's a shortcut. It's a whole lot easier than typing that whole decimal in. On this calculator here, it's right down here at the bottom. I don't have to hit second. Some calculators you have to hit second. On this calculator, it just says A and S at the bottom. Okay. Yours is right above the negative button. Okay. So let's do that. Okay. And so we're going to hit second, square root. And then I want to type the rest of these now. Hit second. Hit second. And then yep. Okay, just to make sure you guys are on the right track, you should get about 52.95, and there's a big, it goes on forever after that, right? It's a big continuous decimal. Is everybody able to get 52.95? Everybody kind of figure out how to do that in their calculator? Anybody need help?
Wait, no.
Okay. Anybody else need help finding that button?
I didn't.
It's a big help. That way you don't have to go back and type that whole decimal.
No, you don't have to punch this one. I just wanted to know if it would like.
Okay, now, I know this one doesn't say how to round, but let's have a little rounding lesson, okay? Because sometimes I think we're not real good at rounding, because maybe it's been a while since we've done it. To the right of the 5 is a 2. So if I asked you to round to the nearest hundredth, what would our answer be?
52.95.
52.95. If this number is 5 or more, we would round it up. If it's less than 5, we would just keep it the same, okay? If I ask you to round to the nearest tenth, this gets a little bit tricky, right? The 10th
53.
is the 9, right? To the right of the 9 is 5 or more. So I got to round this up, which means I got to round the next place value up. So that would become about 53 feet, or meters, I guess it is. Okay? So if I round up this place value and it becomes 10, then I got to round up the place value right next to it as well. Been a while since we've talked about rounding. If this was like a 7 right here, then it would become 8, and then it would be 52.8. Okay, but because it's a 9, I got to knock it back to the next place value before it. And I tell you that because if you're doing big ideas and it asks you to round to a specific place value, you don't give the exact right answer, it's going to count it wrong, even though maybe you've done all the work right. So we got to pay careful attention to what it's asking me to round to. Okay, on this one here, what I would always start with is just draw yourself a right triangle. And I told you that eventually we were going to get to the problems that we did last chapter. We never labeled this side right here because my shadow was never going to be like the suspended height. The shadow is always on the ground. We did a perpendicular height of a statue or a person or whatever it was. In order for this height right here, this is going to be like a support wire. Like if I have like a big cell phone tower, right? A lot of times they've got these support wires coming down to make sure it's not going to fall over. It gets really windy in Kansas at times, so they have to support those towers so they're not going to blow over, right? And so if you're talking about something that comes down at an angle, a support wire is a great example of that. Sometimes this could be like a slide, right? If we were doing like a slide on a playground. This would be the length of the slide, this would be the horizontal distance, this would be the ladder or the vertical distance I'm going to climb up to get there. So there's a lot of different instances. I could talk about like a handicapped ramp. The actual handicapped ramp going up it is the slanted distance, and then you got the vertical distance and the horizontal distance. So those are just some different instances of where we might see something. 5 is the vertical distance here. we're trying to figure out how far from the base of the pole, here's the pole, here's the distance we're trying to find right here. So I'm going to label that with an X. The support wire is 6 feet. Hey. Thanks. So we're going to go 5 squared plus X squared equals 6 squared. Okay, the most important thing is just getting everything in the right spot, right? You got 3 spots, you got to insert numbers. 2 of the numbers we know. What's the third one? We got to get everything in the right spot. Subtract 25 from both sides. Take the square root. Because we're doing a story problem, we want to round, and we're going to round to the nearest hundredth. So we're just going to take the square root of 11 in our calculator. Okay, it's 3.316. And so once again, we talk about we're rounding to the nearest hundredth. The hundredth place value is where the 1 is at. The number to the right of 1 is 5 or more. So then we would round this to about 3.32 feet. Okay.